Yeah, I guess maybe we can start. I don't know if more people will join us or they will find out later this week that the course was on Monday and not Wednesday. But whatever, you're here, so I'm happy about that. And yeah, so I guess some of you were in the GeoPython part of the course, but not everybody, I guess, attended that part, or maybe some watched the video lectures or videos of the lectures. But there's a couple things to announce, just sort of changes for the second half of the course. I mean, when you register in WebAuthority, the whole thing is called Introduction to Quantitative Geology, but practically speaking, the first half is just Python, and the second half now, we've cast aside the geographers and we'll focus on more geological problems. So what that means for us is, one, we have a different website. And so course materials will now be on this webpage, introqg.github.io. There is a link to this website, I believe, from the GeoPython course page as well. So if you've been there, you can get to this page also from that one, and vice versa. Of course, we've linked back to the other page. But yeah, everything that we'll do lesson-wise and links to the exercises, that'll all be here. And the format, I suppose, should look familiar, other than we've changed the color of this little panel up here just to distinguish between the pages. So there's that different website, and all the same information is basically here. If I'm not mistaken, the course details, yeah, so Yorina is also listed here as the teaching assistant, so she'll continue with us here in the second period. And you know, the kind of general course info is all here. Same stuff that's in WebAuthority, but yeah, here it is. Other things that are worth noting, we have, if you were using Slack in the first part of the course, you know, we had these channels for each lesson. We're going to keep doing that, and rather than having a separate Slack for this course, we'll just make our own channel. So like we have QG, so Quantitative Geology, 08 exercise and 08 lesson, just to keep them in numbered order. If you put just 8, it wants to put those at the bottom of the list when they get sorted. So anyway, we'll have these. Does anybody have Slack open? And could you tell me if you see these channels automatically? You don't see them. All right, so at some point, Hendrik found a trick to make it so that you can see them. And I don't think I have to invite you, but there's something I have to do to make it so that you all see the channel. It is a public channel, which means you can join it. And I can invite people to join, but I don't really want to do that by name. Okay, I'll figure out how to make it so that you can all see this. For right now, I think if you go here to browse channels in Slack, so like I just clicked on the thing that says channels here, you should be able to just type in QG and you should see the channels listed there, I think. Does that work? Because it should be public. I did do that, but yeah, I can find it. So you can find it that way. Yeah. So maybe at least for today, if you just want to manually join the lesson and exercise for this week, we'll do that, and then I'll figure out or ask how to do the thing so that you automatically see the channels. There's some setting in here, I couldn't find it when I was trying to do this yesterday, that makes the channel visible by default. And yeah, I don't know. So I do see at least Blauner's joined, and so here we go. So it'd be good if you can join the Slack channels, and I'll figure out how to make them visible by default for the future weeks. So, hi there. So we just got started and was just noting a few differences for those who were present in the first part of the course where we were kind of focused on GeoPython stuff. We have a different web page for this half of the course. Since we've separated from the geographers, we're going to do our own lessons. We have a different web page. So the website's just introqg.github.io. There's a link to it from the GeoPython website, and I don't think there's a link directly from WebOD, but anyway, there's that, and then we've got our own channels in Slack, but they're not visible to everyone, so I'm going to sort out how to make them visible by default. Instead of having these channels like we did for the first half of the course where it's just a number and then the lesson, we have QG for the Quantitative Geology course. I guess Hendrik will also make the same for the automating GIS processes, but that doesn't really pertain to us so much. So, so there's that. Obviously, we're meeting in a different place at a different time, and so at least some of you have found that place. And the other things I wanted to note is are any of you signed up for this part of the course related to English language credit points? So a few? Okay. So if you're not and you're interested, there was not a very large number of people that signed up, so there is still space. The teacher who's organizing that part of the course said she'd be happy to have a few more people. And just as a reminder, in case you're curious, if you're a bachelor student, I guess you have this foreign language credit point requirement. It's something like 4 credit points you need to take during your bachelor's degree. And you can get 2 out of those 4 credit points for English as a foreign language by signing up for this other component of the course, which the name I can't quite remember. But I believe it runs like 12 till 2 or something. Like, kind of follows this, I think, on Mondays. Is that right? Yeah. So, yeah, basically what it would mean for you is it's meant to be integrated in the course. So you would actually be doing things that will relate to the final project that we're going to do at the end of the course, which is you write some kind of scientific paper or scientific formatted paper. And it kind of is a nice way to get a little bit of extra guidance on how to structure the paper and some kind of typical problems that people have when they try to write scientific articles. And yeah, I think it would be very useful if you're interested. So you can still sign up, and I think the first meeting is today, if I'm not mistaken. So I'm just making note of that. Otherwise, for exercises 6 and 7, I guess you mostly all, did everyone get the message that the deadline's been extended until Wednesday? Yeah? So, yeah, we have extended it once and then realized that I was busy with the short course all of last week. Hendrik was out of the country. Volko was out of the country, and that didn't really work very well for you guys getting any assistance when you needed it, because even on Slack we were pretty slow to respond. So you've got a couple extra days, and all of us are now here. I've set aside some time tomorrow afternoon from, I think, noon onward, or 2 o'clock on. What did I put in Slack? I put something. Yeah, 2 o'clock, maybe until 5 or a little after 5. I'm free tomorrow, and then Wednesday morning, if anyone's interested, I could also make some time to give some help with exercises 6 and 7. The important thing for me is I don't want you guys to panic, thinking that this exercise is a lot harder, because it is a lot harder than the previous few. And I think you'll see this week that things are not nearly as hard. The 6 and 7 were new exercises this year, and it happens every time that when we make a new exercise, it's always too hard. And so the exercise 8 that you'll have today, or you'll see at the end of the lesson today, is I wouldn't say it's easy, but it's not nearly as challenging as either exercise 6 or exercise 7. So anyway, if you're interested in getting some help, just post in the Slack thread and let me know. Depending on the number of people, I'm going to kind of post where we should meet. And if we need a classroom or something like that, it'd be helpful if I know about how many people. So, yeah. Otherwise, are there any questions at this point about what's new with this part of the course? Yeah. Okay. So I'm going to close this Slack. And what we'll do then is we'll move on to today's topic. And the lesson's already up on the web page as usual. There's a few things that we're going to go through. And what I would say in general is the format for this half of the course is a little bit different than the first half, because my goal is to only spend maybe an hour or so at the beginning of class going through whatever we need to learn to be able to do the exercise for this week, and then that you guys have more time to get started on the exercise while you're still here, rather than what happens in the first half, which is we spend the entire time going through material and then you start the exercise like after you leave class. So so hopefully, you know, today might be a little bit behind that schedule, but that's going to be the goal, is I don't spend more than about an hour introducing the topic. What that will mean is that for some of the lessons, there's going to be other kind of more detailed material that you can read on the webpage. So I'll introduce the kind of the key stuff you need to know to do the lesson, but there might be more material on the webpage. So as you're working on the exercise, rather, you might want to go back and just read through some of the additional material. So for this week, our focus is on kind of what I've called just basic geostatistics. And so we've already dealt with a few things like calculating mean values using some of the pandas functions. But what we're going to do is kind of take a step back from that and actually write our own functions this week to calculate things like the mean value, standard deviation, just because it's useful to know, one, kind of how to translate an equation into Python, but two, just to actually know what is calculated for something like standard deviation or standard error, because at least for me, I felt like those terms get used, but I didn't really precisely know what they meant. Before we get into the statistics stuff, though, we do have to do a little bit of stuff with NumPy, and so that's where we're going to start, is with this first part, this introduction to NumPy. So this will be kind of the typical format, the hands-on lesson in Spider. So on the course page, if you're following along, and I realize this screen is a little bit smaller than what we had in the old room. If you can't read it, just let me know. So I have all the sort of fonts and things like that in Spider set for like the other bigger room with a bigger screen. But if this is too small, just please say something. So what we're going to do for this part of the lesson is there's this data file, this volcano data. And to get started in the lesson, it'd be good to download that and to extract it somewhere in your home directory. So you can just right-click on it and do Save Link As, or if you're using some other browser, whatever the equivalent thing is to download the file. So I'm just going to download that, and I'm going to put it in my home directory here. And it's a zip file. So I guess probably all of you know how to handle a zip file. But if you want, you can unzip it from a terminal window if you're already. This will need to be bigger. Yeah, I don't know if you're already have a terminal open because you're going to run Spider. This volcano data file, if you're in your home directory and downloaded it there, you can just type unzip in the file name, and it will extract the volcano data file. Or you can just double click on it in just about any other operating system and it will extract. I think Windows does something silly like take you into the, allow you to browse the contents of the zip file without extracting it. So this will create this directory called volcano data, and there's 3 files in there. So there's this volcano or GVP volcano lat lon elev. There's GVP volcano list.xls and then GVP volcano list.csv. This volcano list.xls file is just that's the file I downloaded from the web page when I got the data, and I just converted it to a CSV file to be easier to read into Python. So we're actually going to work with this kind of even more simplified version of the volcano lat lon elev file for this part of the lesson. But yeah, so if you have problems downloading or whatever, just again say something, because otherwise I don't know. So I've downloaded, extracted the files. Now I'm going to go here in Spider and just browse to the directory. So it's just this volcano directory here in my home directory. So I'm going to hit open that and then just hit enter up here. So now if I type pwd to print the working directory, I can see that I'm working in the directory volcano data. If you're in the same situation, then you're good to get started. If not, let me know. So Yorina's not here today, so it'll be a little bit tricky for me to kind of give assistance, but I can. If you're stuck, it's you know, and you want to try and follow along, it's good that that you can. All right, so yeah, let's move on to doing things with NumPy, and I'm just going to start by saying what NumPy is. I think we mentioned it maybe briefly when we talked about pandas a few weeks ago, but NumPy is essentially it's a numerical Python library. So it's really meant for dealing with numbers, with large data files, and dealing with them very efficiently. And with pandas, it's actually what is used in the background to do a lot of the things that happen in pandas. So you'll see that there's some stuff we'll do in NumPy that will look very much like the same kind of thing in pandas. The reason we're not using pandas is that pandas can't do some of the things we need to be able to do. So we're going to deal with some equations. We need to be able to define a list of values where we want to calculate something in an equation, and it's hard to do in pandas. So last year, we taught people how to use NumPy and didn't teach them how to use pandas, and that caused trouble for the geography people when they did the second half of the course. So this year, we taught you guys how to use pandas first, and now we have to go back and learn at least a few things in NumPy. It can do a lot more than what we're going to do, but we'll play around a little bit with NumPy. And we can start by just doing an import. So we'll import NumPy as NP. And this is very common that you rename it to be NP instead of NumPy. And again, we've done the import stuff with pandas. We've done it with other things. So that's no big deal. And then we're going to load our data file, and we're going to load it using NumPy. This will look, again, somewhat similar to pandas, just a bit different, so sorry if it's confusing at first. But for NumPy, instead of read CSV, you use something called load text. and then you say fname equals, and here we're going to give this GVP, and I'm going to hit tab so that it allows me to choose one of the possible files, and we want the top one here. So this GVP volcano lawn elev.csv. And instead of sep to indicate what separates the values, in NumPy you use a thing called delimiter. And it's just going to be a comma in this case. I'll make this a little bit wider for the moment so it's easier to see. So it's a lot like reading data into pandas. It's not going into a pandas data frame, so it's slightly different, but we just list a file name and then we say what's going to separate the values in this file, and in this case it's just commas. It's standard comma separated data file. So if you do that, hopefully you don't get any kind of file not found message or anything like that, and then you can print out the data and you should see something like this. Is that working for most everyone? Any problems so far? We're not going to go through everything in this NumPy lesson because there's some things we don't need to know how to do for this week, but yeah, is everybody able to load the data file? It seemed like the main kind of common issue here was if you're in Windows, rather than having this volcano data that you might have put in some directory like, I don't know, for the exercise or something like that, or this week's lesson, it seemed like there's another volcano data directory, like as a subdirectory there. So if you browse to look for that directory, you'll probably see there's volcano data and then there's another one within that. So you have to go to the subdirectory called volcano data in order to be able to find the data files. And then remember that once you've selected what directory you're in up here, you should press enter so that the IPython console changes to be working in that directory. The other thing is that I did not define a file path for where we're working. So when I opened this data file, I didn't list the full path to loading it. So like if you're over here trying to run a script where you put this stuff, like maybe you've done import NumPy as NP, and then you're trying to do this thing where you define the data directly, this script may not be saved in the same location as where your data file is. And if it's in a different directory, when you run the script, it won't find the data file because it's going to look in whatever directory this the script is saved in. So like this temp.py, I think it's in some place hidden away in my home directory. If I run this, I get this error message that it can't find the file because I haven't told it which directory to look in for this file. We can do that. So like Hendrik showed several times how to do this. So if we just say fp equals, and I think for the Windows users you guys had to put like R and then some location that you could copy maybe from up here. I want to use not this directory, but the one with the volcano data. So I'm going to select this and put in this as my file path. You know, if you're in Windows, the slashes go the other way or whatever, but if you just copy it from up here, you can put in the file path there, and if you want, you can even add the name of the file. So we could put this whole thing here, and then when I go to list a file name, I'm just going to list FP as the file to load, because that's going to tell it to load whatever's in this /users, WIP, volcano data, blah, blah, blah. Does that look familiar? You guys have done this a couple times now. So if you do it that way, then you can be sure that when it tries to load the data, that it will find, no matter where the script is saved, it will find the data file, because you've listed the complete path to where that data file is stored. I don't often do this because I tend to put my scripts in the same location as where my data is, but it's actually not a bad idea, because now if I move the script, it doesn't break. But again, remember, if you're in Windows, you got to use the / going the other way, and you'll probably have a C, like something like this, blah, blah, blah. But this should work now if I run the script. And sure enough, it looks like it does. So anyway, I'm going to be typing stuff in down here, but hopefully you've been able to load the data file. It's not totally critical at this point that you have, but because you can just watch. We're going to get to practice with this stuff in the exercise for this week. But yeah, so we've loaded our data in here, and when I print out data, I get these numbers. I'll make this just a little bit wider so we can see. So it's a little bit different than what we had in Pandas. In Pandas, we often had some kind of name of the columns. We had then the data that was associated with that name. So it might have been something like temp, or station ID, or something like that. Here, right now, what we have is just numbers. And if we look at the type of data, what you see is it's this data type called a NumPy.nd array. So this is a NumPy data format. A data series in Pandas is almost identical to this, but this is a little bit different format than what we've dealt with before. And here, we can give names to the columns in NumPy. We're not going to do that for our purposes today, but you can. But all we have is numerical values here. So our data file didn't have any labels for the headings of the data here. It's just numbers. And so you have to know a little bit about what's in the data file to be able to deal with it. And that's just the reality of dealing with this kind of data file in this case. So as I mentioned in the lesson for today, there's more stuff than what we're going to cover. I'm going to skip over some things in NumPy that we've done previously in Pandas. Like if you want to know how big your data file or how big your data is that you've loaded, you can get that information just like you can in Pandas. If you want to know the data types of the data in the file, you can also get that. And you can do conversion from, like, here you can see we have numbers that are decimal values. We could convert those to integers if we wanted to. But we're not going to do that for today. You can see how to do it on the web page. It's not something we need for the exercise, so we're going to skip it. And just like with Pandas, we can do data slicing. In fact, I think this is more intuitive to do data slicing in NumPy than Pandas, but that's probably because I come from this kind of background that I'm used to storing data in these kind of arrays. So you can take things like data 0, 0. So the square brackets, remember, that's how you're going to use an index value to refer to the location of something in data. And if I do data 0, 0, I get this first value in the top left part of this data array. So I get the value in, I think it's row 1, column 1. But since the index starts at 0, it's row 0, column 0. We could test that out if I do data 0, 3, I expect to get something like 600. And sure enough, so that's first value is row, second value is column. So we can kind of slice our data up that way. We did a little bit of data slicing stuff in Pandas as well. If we want to get something like the first 2 columns and the first 5 rows, we can do that in Python with NumPy pretty easily. So we say first 5 rows, first 2 columns. So here we just use this colon character to separate between the starting value we want and the last value we want. And this is like the range function, if you remember how range works, that it never includes the last value. So this will give us index 0, 1, 2, 3, and 4, but it won't give us index 5. And same thing goes here, that we get columns 0 and 1, but we don't get column 2 because the last value that's listed here, it's just like range that you don't include it. So now we see the first 5 rows, the first 2 columns by using this index slice. This stuff is super, super useful to be able to slice your data and extract it, because you can also do things to the data slice exactly as you could to a full NumPy array. So we'll see an example of that in just a moment, but I guess this idea of doing the slicing is already somewhat familiar, because you guys had to do some of this stuff for like getting the range of different months that were in a certain season. You had to do some time slicing to do that. Here we're just, our index value is not some date, it's just a number. And so we're just using that number to take out some piece of a larger data set. If we wanted to get all of the columns for the first 5 rows, you can actually list just a colon with no value on either side of it, and that will give you all of the values that from the start to the end. So now you can see we get these 4 columns in the first 5 rows. So this, I guess, at least in terms of a concept, should be somewhat familiar. Yeah? Okay, we got 1 nod. Can I assume you guys are familiar with this idea of slicing the data? Is that safe to assume? Because if it's not, you can tell me, and I don't mind to sort of review it. Otherwise, I'm going to move on. Okay, we'll keep going then. So again, you'll get to practice, I think, a little bit with this data slicing this week. But one of the things that we might want to do is, in this particular data file, it happens that the second column is latitude for where these volcanoes are located. I haven't told you anything about the volcano data at all. But in the data file, we have 4 columns. The first one is some ID number that's assigned. Second is latitude. Third is longitude. And the fourth is elevation of these different volcanoes. So you can do things with the data slice, like say latitude equals data. And we want to take all of the rows for the second column. So remember, with the indexing, you got to pay attention. Starts at 0, so second column is going to be index 1. And so that will just take that 1 column and assign it to a variable called latitude. And if we print out then what latitude has in it, we'll see a bunch of numbers that look more or less like latitude values, right? They're in degrees and between plus and minus 90 as far as we can see. So checks out. Should be okay. You know, if we got values that were 360 for latitude, we'd have a problem, because you know that's outside the range that we expect. So anyway, that's that. And I think maybe I'll flip things around a little bit in terms of the order of the lesson on the website, and just show you a couple things here at this point with latitude. So if we wanted to find out whether our latitude values make sense, one check is to say, are they between plus and minus 90 degrees? So we could take something like latitude and do latitude.max. So this is like pandas, that you have these built-in things called methods. These are functions that can operate on any type of data that's stored in a NumPy array. So we have a max function, and I think you guys probably can guess what the max function does. It's going to find for us the maximum value of latitude. In this case, it's 85.6 degrees. So far so good. It's less than 90, so that's what we need. And same thing goes that we have a min function. So if I do latitude.min, I find the minimum is minus 78.5. So what it looks like is, at least at first inspection, the numbers we have make sense for values of latitude. So if we'd chosen the wrong column or something like that and called it latitude, that might jump out at this point, but it looks like everything's okay here. If for some reason you wanted to know the mean value, you can also do mean. I mentioned this one because you'll use it this week in the exercise. So any NumPy array.mean will give you the mean value. And here we see the mean value is a little bit north of the equator, so 14.05 degrees north. And that's probably not a huge surprise. I don't think that volcanoes are necessarily geographically biased to favor the northern hemisphere, but most of the land mass on Earth is in the northern hemisphere, so there's less land area for volcanoes in the southern hemisphere. So that's not a big surprise, maybe, that the average latitude's a little bit north of the equator. So again, I guess this kind of thing, using these methods, is something that's somewhat familiar from pandas, right? Because you guys even did this exact same thing in pandas. In fact, in pandas, it's just using NumPy in the background, but you don't know that. As a pandas user, you wouldn't see that it's using NumPy, but it's doing all the kind of calculations on the back end with NumPy. The reason that we're learning this at all today is because of the two things I'm going to show you right now that pandas, as far as I know, cannot do. And there are things that we need to be able to do. And one of them is to define an array with values that start at some number and end at another number with a certain number of increments in between them. So we've seen something kind of like this with the range function, that we have some starting value and an ending value, and maybe we specify the step in between. So we could define a variable called x, and we're going to use a function now called np.linspace. So this is, I guess, probably a shortened version of linear space. And what linspace expects is, as you can see here, a start number, a stop number, and then the number of steps in between. So we'll do it this way. We'll do from 0 to 2 times np.pi, just to show you that the value of pi is known within NumPy. It's just np.pi. I think that's fairly intuitive. So 0 to 2 times np.pi, and we'll do 10 steps. So this is going to create a NumPy array called x that will start at 0, that will end at 2 times pi, and will have in it 10 values, if I'm not mistaken. So let's do that, and then print x. So when I print it out, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. So far, so good. Looks like it starts at 0. That looks like 2 pi. And there we have it. Why would you want to do this? Well, I could show you one good example for why you might want to do this. Oops. And that is that, let's say you wanted to calculate the sine of x from 0 to 2 pi. It's sort of a simple kind of toy example, but you could say y equals np dot sine but if I defined, maybe just to make the point here, x to have 11 values in it, then x at position 5, which is the middle value in this case, is pi. So when you include the starting and ending values, this is one of the things that you'll deal with. Yeah, so this linspace thing is pretty useful because if you want to create an array that starts at a certain value and ends at another value, and you say, I don't care necessarily what the size of the increment is in between the values. I don't care if it's some 2 pi over 9, which is a really unusual subdivision of the space between the numbers. All I care about is that it starts at one number and ends at another one, and I want this many values, then linspace is the way to go. There's an alternative that you can do the same thing. Actually, maybe just to go back for a second, because I was in the middle of why we would want to do this at all. But we wanted to calculate the sine of x before I got kind of sidetracked. So you can do that using y equals np dot sine of x. You could call this whatever. These are just variable names, so you could call them whatever you like. But we can calculate the sine of x simply like that. And if I print out y, I see that it starts at 0 like the sine should. Sine function should start at 0. I can see it goes up like it should to around 1. Doesn't quite get to 1 because we have, again, an even number of subdivisions. No, actually, we have an odd number now, so it should at some points get very close to 1. Anyway, it goes up, comes back down to around 0, goes negative, and then comes back to around 0. These values aren't exactly 0, but you can see they're pretty close. Anything times 10 to the minus 16 is pretty close to 0. So that's our sine function. When you guys are going to do things in this part of the course, there will be cases where you use some equation and you want to calculate the values, for instance, of temperature at different depths in the Earth. So you might use this linspace to define the range of depths where you want to know the temperature from the surface maybe to 50 kilometers. And you say, okay, maybe I want to know the temperature at every 1 kilometer interval. So I could say something like, z for depth equals np.lin space. And I'm kind of going off the script here. But we could say it starts at 0, goes to maybe 50. And again, if I want 1 kilometer spacing between the points, I need 51 subdivisions, 51 points. And then if I print out z, what I see is that I get evenly spaced numbers from 1 to 50. If I did the same thing with only 50 points, I'm going to get something divided by 49, which is going to give me some nasty repeating number thing, or actually even worse, this kind of messy values. So this is 50 subdivisions starting at 0 and ending at 50. So again, maybe this helps just to kind of see the point that if you want to have even increments, you have to have one more than the number you want to go to. Anyway, these are just, an example where if we had defined this range of values of depth, we could then use some function to calculate temperature at each one of those depths. That's the kind of stuff we're going to do here And so this is where it's a little bit different than like what the GIS people do and why we didn't teach this stuff in the first part of the course this time. I think I've said about enough about NumPy. Well, all right, I got one other thing I should show you. Let's define another variable called x2. And we're just going to define this range of values using one slightly different function in NumPy for creating arrays. Here we're going to use np.arange. And like linspace, you have a start number, you have an end number. But here, instead of the number of subdivisions, you list the increment between the values. So we can start at 0, go to 2 times np.pi. And let's do that in steps of 0.5. So this will find me an array of whatever length is required that starts at 0, ends at 2 pi, and has separation between the values of 0.5. So if I print out x2, I see 0, 0.5, 1, 1.5, 2, blah, 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 all the way up to 6. 2 pi is around 6.28, so that's smaller than 6.5, so we're not going to get 6.5 included in this list. If you want to make arrays that have constant space between the values, this is one good way to do it. But I will show you one kind of cautionary thing, and that is, let's say instead of going between 0 and 2 pi, I wanted to go from 0 to 10. Actually, let's go from 0 to 5 in increments of 0.5. I'm going to do that and print out a range. You might have expected to see 5 included in this list of values in x2. This arange function, again, works just like range in Python, that it does not include the last value that's given here in the list if it's exactly equal to one of the increments. So this is a little sort of subtle thing, but at some point, once the video is up for this and you're working on the exercise, there is a good chance that you're going to encounter this problem saying, I want to have exactly the spacing between my numbers of this, and I'm going to do that by using arange, and you're going to make your array and find that you don't get the last value you expect. And then it would be good to come back and take a look at this part of the lecture. If you make it 5.1, then you get 5 included in that list, because 5.1 is greater than 5. So when it goes to calculate that last increment, it says, okay, it fits within the range. If the value is exactly equal to that last value, it will be excluded, just like the range function does for making lists you often use for for loops and things like that. So I know this is kind of boring stuff, but it's maybe worthwhile to mention just because you're going to have problems with this, most likely, if you use this arange function. I basically prefer to use linspace in almost every situation because I like to know my starting value and ending value are always included. More often than not, I don't really care about what the space between the points is. And if it matters that much, then I take the extra minute or so to think about it and make sure that, you know, if I want from 0 to 50 in 1 kilometer increments, then I go, right, I need 51 subdivisions, not 50. I think linspace is safer in my opinion, but that's that. So there's also a note that there's other things like xmin, xmax, xstd, which is standard deviation. And one thing I can show you that's kind of cool is if this is x here, you can take a slice of x. So let's take the first 5 values of x. That's this. And you can also do the mean on that. So I can take a slice and use these same things. I could say, you know, that slice dot min or dot max. That's kind of cool. So it's nice that you can take these slices and still use the same built-in functions to do calculations with NumPy. Are there any questions? Have I totally freaked you out about this? You'll have time to practice with it in the exercise, and basically all of the exercises from here out will use some NumPy. We don't really do anything that's super deep in NumPy, so it's really mainly using things like arange, the sine function, cosine, whatever. So if it's a little bit uncomfortable now, that's okay. But if it's, if you're panicking already and debating whether to leave like some of the other people have, you could maybe let me know and I could try to help before you get yourself too worried. It's not that bad. People survived last year. So, okay. So with that, then unless there's any questions, I'm going to kind of take a break from the NumPy stuff and jump to our topic for today. I know we're running a little bit behind schedule, but that's kind of expected for this first day because the NumPy stuff takes a little bit of time. So I'm going to go here back to the course page and just highlight a few things about this geostatistics lesson. What I'd like to do is just make the suggestion to you that you take a little bit of time and read through this when you have some free time to get some more details here. There's some useful things just in terms of terminology that are presented here about making a distinction between a population of some thing, could be, these little critters, and a sample of that population. These sort of statistical terms that are used and, in my opinion, often misused by scientists who are not statisticians. So I'd say it's worth your time to read through it. At some point, what I'm going to show you is just a couple highlights of things that you need to know for the exercise, and then I'm actually going to try to get to explaining the exercise here relatively soon so that you can have some time to get started, and I can be here to help out with that as you get started. So have any of you actually had a class previously on statistics? One? Okay. Because it's kind of scary for earth scientists that not all of us have statistics courses, because we're probably among the worst in terms of having to deal with uncertainties and making some sort of scientific conclusion about an extremely limited subset of data from some location. In the past, I showed examples of field photos from places where there's essentially no vegetation, there's no soil, and it's almost all bedrock at the surface. For most geologists, we're like, oh, awesome, we can just go to any outcrop we want, which is essentially everywhere, and measure whatever we like. But of course, at the Earth's surface, even if there's no vegetation, we only see a tiny amount of the total rock present in some formation or some bedrock unit. So in terms of accessing that amount of rock and actually being able to randomly sample it in a truly random way, we can't, because more often than not, we'd need to go, drill down 200 meters, and well, that's expensive enough when you drill one hole, but to go around randomly sampling locations at random depths, in many cases you simply can't do it because it's not accessible to get the equipment there or whatever. So we have a big problem in terms of doing random samples. Other sciences don't necessarily have this problem because they might actually have access to an entire population of of something you might want to take a subset. And in fact, like a good example here is the public health statistics in Finland. Like, people are super good about filling out surveys here, and when information is requested, they've got like incredible response rates compared to many other countries in the world. And so some of the the data that they have here is rather famous because of the fact that the sample is covering so much of the population, whereas in a lot of other places you just don't get enough people responding. It might be good to get 30% of the people you sort of send your survey to actually respond. And I think in many cases here it's far higher than that. I mean 80 to 90% I think in certain areas. So that's kind of pretty incredible. So this is the example idea of some of the trouble you can have with taking samples of a population. So first off, this is what we would call the population. This is all of these creatures of some, I don't know, I'm not a sort of paleontological type, but it looks like there's like brachiopods and some kinds of corals and trilobites and stuff like that here. And let's say we had access to every single one of them that lived during a certain period of geological time. We could take a random sample of some number of those creatures, and here what we see is that just by sampling randomly in one case and another one, we get very different sizes in terms of the average size of the creature that we've sampled. So these are mostly big, and these are mostly small. And this is one of the issues you have when you take a random sample, is that you don't necessarily get one that represents the whole population. Here you might conclude that there were no small creatures that lived at this time, or here that there were no big creatures that lived at this time. And that's just by chance. You just happen to have selected all small creatures by random chance, and that happens. So you know, these samples, it's just some group that's taken out of the population, and the hope is that that population is represented by the sample you take. I guess that idea probably is somewhat familiar. Another possibility here is that you have different populations. So if we look here, we have one population that looks like this, one that looks like that. I think we can agree those look like different populations. But again, by random chance, you could have two samples that look very similar. And so you could conclude, of course, then that these two, you know, creatures living at this time and creatures living at this time must have been, you know, swimming back and forth to each other's houses, or whatever happens with trilobites. But you know, the conditions were very similar for these creatures based on the samples, when in fact the samples are not representing the populations on average. Now that's what happens in the case where you actually have access to the whole population, which, you know, that is something that geologically speaking we don't ever have access. Even with the creatures that are alive here, right? There were many, many more of these things that lived than actually got preserved. So, you know, if these guys lived by the beach, it might have been a nice place to be living, but of course, beaches aren't good places for preserving even, you know, critters that have hard shells don't necessarily survive on the beach. They tend to get washed and shells break down as the waves smash them against the shore. So, you know, we have a preservation issue here, as well as the fact that, like, we just may not have access because the exposure of where we can collect these guys might be quite limited. So there's problems, and you can read maybe a little bit more about that if you like on the course page. There's also issues of uncertainty, and uncertainty for us, we can kind of break this into two classes, and the two different or the sort of distinctions we can make with uncertainty is between precision and accuracy. So again, on the website there's some more of these terms defined, and I'm not necessarily concerned that you're going to remember them all right now, but if we know what value we can expect, if we know what value we should get, then we can make an assessment of whether or not what we measure is accurate. So if we took some standard material with a known geological age, and we took it to some laboratory and measured its age, we have an expected result, and if we get an age that's much different than what we expect, we can say that the measurement was not accurate. we can also do things like this, where we talk about whether we have, random or systematic errors. So, the random error would have to do with how well the value represents the expected value, or I'm sorry, I guess that's the systematic error in this case. So here we can see all the points falling within the bullseye where the random error is small, the systematic error is small. Here the random error is small, so the points are clustered closely together, but they've drifted systematically from where we expect them to be. So they should be in the center of the bullseye, instead they're over here. So we have some systematic offset. This could be that your machine is not calibrated properly for measuring the ages. So it's doing a good job of repeated measurements giving the same age, but maybe it's got some kind of problem otherwise that results in consistently being off of the expected value. And of course you can have problems where the random error is big, so the variation between points is large, and on average you're still close to the middle, or both. The problem as geoscientists is that we can have some assessment of things like random error, but systematic error is something we don't often know. If you take a random rock and you measure its uranium lead age, do you actually know beforehand what the age should be? Probably not, because that's why you're doing the measurement. So you don't have the bullseye, in other words, to know whether your measurement is accurate or not. All you know is that if you measure the age again from another zircon in the same sample, if it repeats that age over and over again, you say, okay, well, at least our random error seems to be small. We don't see much difference in the measured age from measurement to measurement. But you still don't know whether you're just off by 100 million years. So this is the reason why labs that measure ages for geochronology use standards, because they have to have some way of knowing, is the equipment off, or is it giving the right number? So if you take a sample where you know what the age should be, and you measure it with your equipment, if it doesn't give that age, then your equipment has a problem. So anyway, again, these terms are a little bit discussed in more detail on the webpage. There's also some stuff here about reporting measurements and how to report measured values. So this kind of standard thing. Probably saw some of this even in high school about like saying your best estimate of the average value plus or minus some uncertainty as the way you report a measurement. So this best value could be the mean of all of your measurements, the average, plus or minus some uncertainty, which could be the standard deviation. Those things are all defined here. So we calculate the mean value. You guys know how to do that probably without seeing this equation, but here it is in equation form. I'm sure that if I gave you some assortment of numbers and said find the average, that you could do that. But you might not do the other problem, and that is to say, if I said here's the average value of these numbers, what's the equation I use to find that, you might not come to this. And so there's that. There's an equation for the deviation and then standard deviation. There's two different forms of standard deviation that are shown here, and we can talk about that if you'd like, but you're going to play with these equations in the exercise for this week, so you'll come back to seeing these guys. There's also the standard error that's defined here. And I think for our purposes today, I guess when I say standard deviation, is that somewhat familiar to you? I mean, the average value, I guess, is that one everybody knows. Standard deviation is just some measure of how far the measurements deviate from the mean. So how far away they are from the mean value on average. So if every single one of your measurements is exactly the mean value, the standard deviation is 0. That's never going to be the case for geological material, period. But anyway, this equation basically just sums up how far each individual value differs from the mean. So that's what this summation is here. There's some stuff about the sigma notation. If you don't know what this sigma means, don't panic. There's a hint on sigma notation in the hints for exercise 8. But you sum these values together, you square it, you multiply by 1 over n for the number of values that you have. So if you have 10, this would just be multiplied by 1 over 10, and then you take the square root. That's the standard deviation. You can't just take the average of the deviation because that's 0. So deviation is just the given measured value minus the average. And if you add all of those together and take the mean, it gives 0. So that's why the standard deviation involves squaring the value there. And the difference between this and this is not critical for us. So standard error, I guess maybe you've heard the name before. It's just standard deviation divided by the square root of the number of measurements. So as you have more and more measurements, even if the standard deviation doesn't change, the standard error will get smaller. So this is the idea that the more you measure, that your uncertainty should go down somehow. So you'll sometimes see standard error reported for age measurements, for instance, in geochronology. And our last bit here is just about the normal distribution. Again, I think you can read through this, but I guess you've probably seen these kind of Gaussian probability distributions before, maybe? Yeah? So this is essentially just representing, in this case, these are cinder cone slope angles from some kind of, simple example. The average would be the vertical bar here. You can see they go from 0 to 70 degrees. And there's, of course, values that say the probability here is most likely that you get the mean. If you just took a random cinder cone, it's most likely going to have a slope near the mean. And that as you go further and further away from the mean, you're less likely. So this is probability or frequency along the vertical axis. So out here, at very low slopes, you're unlikely to have very many of your random cinder cones with a low slope. Most of them will be close to the mean, and then same thing goes that you won't expect many to have a high slope. And so you can see in the figures here, visually, like what this is plus or minus 1 standard deviation from the mean, plus or minus 2 standard deviations. Maybe you've seen some of these things before, but we'll also look at visualizing some of our measurement uncertainties in the exercise for this week. So that was kind of a whirlwind tour of the basic geostatistics stuff. Some of it's probably already familiar, and if not, please just take 10 minutes and read through the web materials. It may make your life easier when you come to the exercise if you have a kind of clear idea of what some of these terms are. So with that, let's go here to the exercise. So this is exercise 8. This should look kind of familiar. We're back here in GitHub. And there's 2 problems for exercise 8. The first one basically is just converting equations into Python code. So that's one of the goals for this part of the course, is to learn how to take an equation and write a Python code to handle that equation. And here you're going to create 3 functions. One to calculate the mean value using this equation, one to calculate standard deviation using this equation, and then one to calculate the standard error using this equation here. As was the case before, you can certainly calculate here, for instance, standard deviation, and then plug that into the function to calculate the standard error. Or use your standard deviation equation to calculate your standard error. But basically, you'll write these functions up so that if the user gives some list of numbers, that it would return the mean value of that list of numbers, and or the standard deviation, standard error. So that's the main task here. And you're going to write these into a Python script called geostats.py. And to show that it works, you're going to use this age data here. So these are rock samples that were measured for thermochronological ages. Don't worry if you don't know what that means. but from the Himalaya and Bhutan. So in each sample, there were, for instance here, 5 ages that were measured out of 1 rock sample. And then 5 that were measured here, 2, 5, and then 4. So what you're going to want to do is you can make, we're not going to read in a data file here, you can just make Python lists with these numbers in them, and you don't even need to have this this sample ID column. You could just make a Python list called BHF04 and have it have 2.21, 5.1, 2.93, 4.96. So you'll make those Python lists, and the idea is then that you can use your mean function with these values, and it should give back the mean value, or the average, of those 4 numbers. So you'll plug in, I guess there's what, 5 samples here? So you'll make 5 lists, and then you're going to put each list into your function and show that the mean value you get back is what you expect, or the standard deviation, or whatever. So, so you do that, you'll test your functions, and then after that, you can use the np.mean, np.standard, and np.square root. So there is no function for calculating standard error, but if you can calculate the standard deviation and the square root, then you can calculate your standard error. So this is just to sort of cross-check with NumPy that the mean values you get are right. So if you take your list and then plug it into the np.mean function, it will give you the average value, and that should be the same as what your function does. Does that make sense? Yeah? I mean, you could also do this by hand and just calculate the mean, but probably calculating the standard deviation by hand is a little bit more of a pain. And it's nice just to say, well, NumPy should be right, so I'll put my list in NumPy and see if I get the same numbers. And then you can just print things out to the screen using the print function. So that's problem 1. There's a few questions after that just about kind of, what do you see in the age data? But I guess that get some idea what you're going to do for problem 1. Yeah. For problem 2, we get a little bit nastier looking equation here. So sorry about that. But this is the equation for calculating the normal distribution of error. So this will be like allow you to plot one of those bell curves for a given measurement. So the idea here is that you can use your mean that you'll calculate in problem 1, your standard deviation values for this age data from problem 1, and then you're going to plug those into this equation and make a plot of the probability distribution. And in fact, I'll show you at the end here in the hints, there's an example plot so you have some idea what you're supposed to do. So you have these output values, you have this equation that you're going to use, and here, for instance, you're going to need to create some array, in this case of values of x, that defines all the points where you want to calculate this probability distribution. So if I go just back to the lesson for a second, to here, to this plot of the normal distribution, what this is essentially between 0 and 70 degrees. At each point, we calculated what's the probability of there being a cinder cone with this slope. And you see it's basically 0 up until, I don't know, 20 degrees or something like that. And then it starts to slowly go up, reaches a peak at maybe 35, and then starts to come back down. But in order to make this curve, you have to calculate the probability at each one of these points based on the measured values that you have. So that's where you need to use this linspace function, because you have to basically define, in our case, it's going to be the range of ages where we want to calculate the probability. In that other example, it was the range of slope angles. And then you'll use this equation to calculate the probability at each one of those ages. And there's a good number of hints in the exercise hints based on last year that should help you if you get stuck with any of this. So you'll make your little function here called Gaussian that does this calculation. You save it in your geostats problem 2 Python file, and then you'll do your calculation of the probabilities, and then make a plot of the output. So we'll do this using matplotlib, not using pandas for plotting, because we'll probably not use pandas for plotting for the rest of the course. So sorry if you've fallen in love with plotting things in pandas, but we're going to use matplotlib because that's what I'm much more familiar with, and so it's easier for me to give you help with matplotlib. So you make a plot. There's some stuff that goes on the plot, and I'll just show you the example in a second. You've got a couple questions, and then some space down here to put your answers like normal. So in the hints for this week's exercise, that's just the link I clicked. Here's some stuff about the sigma notation. If you've not seen it before, kind of how numbers are summed up and what it means. And then for problem 2, here's the thing you probably care about most, and that is the example plot that you're going to make. So what you end up doing is you make these little, I guess you can see them pretty clearly, these kind of bell curves for the different measurements. And then you plot up at the top of each bell curve the mean value and then an error bar showing what the standard deviation is. So it kind of helps you see that, you know, this is essentially 2 different ways to represent the uncertainty in a measurement. When the standard deviation is quite small, you see that the probability of getting the value is very high, and you get this kind of high spike. And here, for instance, where the standard deviation is very large, you have this very broad and low probability curve, which essentially says that, you know, effectively you're equally likely to get any of these values. Okay, it's more likely you're going to get one near the mean, but this is very broad. Whereas if you said, okay, what's the likelihood that I get a value of 4 million years for this sample, it's basically 0. So that's the plot you'll end up making, and the idea in general is just to kind of take a look at different ways in which we can visualize uncertainty in our measurements. So you do the calculations, then you make the plots. And that's it. So it's just those 2 problems. I'm not going to say it won't take you a bit of time to do that, because that would be just unfair to give you that idea. But I hope that it won't be anything kind of like exercises 6 and 7 from the GeoPython part of the course, because I know those were stressful for a lot of people. As you can see here, there's lots of hints. This is the same exercise I did last year, so I've tried to not make too many changes since it seemed like it worked out all right last year, but people did need some hints, and so you have them there if you need them. With that, I think it's past time when I should stop talking and let you start working, but I just can ask if there are any questions first before we stop.